Binary search fails in real programs when someone copies the loop without understanding what the search boundaries are supposed to mean. The usual misconception is that binary search is just a faster way to check the middle of a list. What actually makes it work is the guarantee that a sorted order lets one comparison eliminate an entire region of possible answers. Picture debugging a search that keeps returning not found, even though you can see the target sitting inside the list. Start with the simplest mental model. You have a collection arranged in sorted order, and somewhere inside, it is the value you want. Instead of asking whether each item is the target, binary search asks a more useful question. Which side of the collection could still contain the target? That change in question is the whole algorithm. Imagine a customer list sorted alphabetically, and you are searching for Maya. The middle entry is Noah, so Maya cannot be anywhere after Noah in an alphabetically sorted list. You do not need to inspect those later names at all. The ordering has already proved that an entire section is impossible. Now the search is restricted to the earlier section. The new middle entry is Grace, and Maya comes after Grace, so everything before Grace can also be discarded. The search region has become smaller from both directions. When the new middle becomes Maya, the search ends because the remaining question has finally been answered. Notice what happened during that search. Binary search did not move toward Maya one position at a time. It kept changing the definition of where Maya was still allowed to exist. Every comparison either finds the target or makes part of the collection permanently irrelevant. That is why a binary search implementation usually tracks three ideas: a left boundary, a right boundary, and a middle position. The boundaries describe the part of the collection that is still possible. The middle position is simply where the next decision will be made. Thinking of them this way is much safer than memorizing a loop. Suppose the middle value is greater than the target. Because the collection is sorted, the middle value and everything to its right can no longer be the answer. The right boundary, therefore, moves to the portion before the middle. Nothing on the discarded side should ever be searched again. If the middle value is smaller than the target, the opposite happens. The middle value and everything to its left are ruled out, so the left boundary moves past that region. The algorithm then repeats the exact same reasoning on the smaller interval. This repetition continues until the target is found, or there is no possible interval left. There is a useful invariant hiding underneath all of this. Before every comparison, the current interval represents every location where the target could still legally exist. After the comparison, the algorithm throws away only locations that the sorted order has proved impossible. If that statement stops being true at any point, the implementation is broken, even if the code looks close to a textbook version. That last case matters because binary search must also prove when a value is absent. If the left boundary moves beyond the right boundary, there is nowhere left for the target to be. Returning not found is now justified by the search process rather than by reaching the end of the collection. The algorithm has eliminated every possible location. The most common beginner mistake is using binary search on unsorted data. If the values are not ordered, seeing a middle value greater than the target tells you nothing about which side contains the target. A smaller value could still be on the right, or a larger value could still be on the left. Discarding either side would be a guess. The correction is specific. Binary search only works when the property you are comparing is ordered consistently across the search space. A list sorted by username can support binary search by username, but that same ordering does not automatically support binary search by account age. The algorithm depends on the ordering relationship, not merely on the fact that the data happens to be stored in an array. Another beginner mistake is updating the boundaries incorrectly. If the middle position has already been checked, leaving it inside the next search interval can cause the same position to be checked again. In some implementations, that mistake creates a loop that never shrinks. The practical test is simple. After every unsuccessful comparison, the next interval must be strictly smaller than the previous one. This gives you a useful way to debug binary search without staring at code syntax. Print or visualize the current left boundary, middle position, and right boundary on every step. Then ask whether the target could still exist anywhere inside that interval. If the answer is no, your boundary update discarded the wrong region. If the interval does not shrink, your update did not discard enough. The reason this algorithm scales so well is that the search space keeps being cut down rather than reduced one item at a time. A linear search grows directly with the amount of data because more items can mean proportionally more checks. Binary search grows logarithmically because each decision removes a large fraction of the remaining possibilities. The important difference is not that one loop is written more cleverly, but that one algorithm extracts more information from each comparison. This also explains why binary search is not automatically the best choice for every lookup. Sorted order has to come from somewhere, and maintaining that order can have a cost when data changes constantly. If you only search a tiny collection once, a simple scan may be easier and perfectly adequate. Algorithm choice depends on the full pattern of work, not on choosing the method with the fanciest complexity label. The deeper lesson is that binary search is really an elimination strategy. The array version is only the easiest place to see it. The same reasoning appears whenever a problem has an ordered range and a test that tells you which side can be ruled out. Once you recognize that pattern, you can use binary search ideas to find thresholds, boundaries, and answers that are not stored as literal items in a list. So do not memorize binary search as a recipe that says, check the middle and repeat. Remember the invariant instead. The target, if it exists, must remain inside the current search interval. Every comparison must preserve that truth while making the interval smaller. Once that mental model is clear, the code becomes a direct translation of the reasoning. The next lesson is big O notation, because binary search becomes much more interesting once you can describe precisely why cutting away half the remaining work changes how an algorithm behaves as the input grows.